All right, section 2.1, one of my favorites actually, is called reasoning and logic. So you mentioned, Jessica, that you guys are in critical thinking. Is that what I heard? Some of this is going to feel like that. Some of this chapter in general, this chapter 2, is going to feel like stuff from critical thinking. I don't know if you're there yet or not, but at some point you're going to feel like I've seen this somewhere recently. All right, so the first thing we're going to talk about is a little bit of vocabulary so that we're all on the same page. First one is a statement. A statement is simply a sentence that is true or false. So what I'm going to do is I'm going to give you an example and a non-example. So an example of a statement is something like this. I ate eggs for breakfast. It's either true or it's false. There's no middle ground. You're not sort of ate eggs for breakfast. Either did or you didn't. Okay? A non-example. Something that is not a statement. There's a couple of things that I'm going to write here. One of them is something like this. What did I eat for breakfast? This is not a statement because it is not true or false. We call this a question. I know you guys know that, but my point is that a question is not a statement. A statement is an assertion of something that's true or false. Questions don't classify as that. Another thing that doesn't classify as that is this, something like, go eat your eggs for breakfast. We have a way that we refer to this too. Do you know what we call it? It's command. Commands are also not statements because this sentence, it's a sentence, right? This sentence is not a true or a false. It's a command. It's a directive. It's telling somebody to do something. So it is not considered a statement. All right, negation. A negation is the logical opposite of a statement. And it is written tilde P. So if the statement is written P, then the negation is written tilde P. Okay? It's the tilde part that makes you to negate something. Sometimes negations are very straightforward. So we're going to use my statement above that really was a statement, right? That I ate eggs for breakfast. What do you suppose the negation of that would be? Yes, I did not eat eggs for breakfast. Okay, now if that's as far as we went with this, you just put nots in things, or you take nots out. If I said I did not eat eggs for breakfast, then the negation of that would be I did eat eggs for breakfast. Okay, so that would be fine. But negations get a lot trickier, not a lot trickier, but they are trickier when they have things called quantifiers involved. So let's talk a little bit about quantifiers, and then we'll see how these two things interplay. The first kind of quantifier is called a universal quantifier. Universal quantifiers refer to each and every element in a set. They use words like all, every, no, or none. Universal quantifiers are probably the ones that you've gotten in trouble with your parents for. Where you said something like, you never get me ice cream for, my birthday. You never. You always get mad at me when I do this, right? These are the words that get us in trouble. Existential quantifiers refer to one or more elements in a set. They use words like some, at least one, or there exists. Okay? So I'm going to give you an example of each of these so that you can jot them down just to remind yourself of the kind of sentence you're looking at here. A common one, you've all heard this before because I'm just sure you have. All boys love their mama. You heard that before? I don't think necessarily is true, but probably mostly true. You've heard ones before, like all dogs go to heaven, right? We hear these words, these phrases with the word all a lot. An existential example would be something like this. Some people like swimming. Doesn't say all, it just says some do. Okay. Could it mean all do? It could. Some could mean everybody. It doesn't mean you know what the other people do or don't do. You just know that some of them do. Okay? All right, so as I mentioned, and it's written in your notes, it's not written on the slides, but creating negations when quantifiers are present takes more care than when they're not. So I'm going to give you some examples so you can see how that works. And so here's my all dogs go to heaven example. We're going to write a negation for each of the following. Okay? So jot yourself a note down here about this. When you have universal and you have existential and you create negations, these always change to the other type of quantifier. So all is a universal quantifier. Whatever I write down next has to be an existential quantifier. Has to. I can't go from all to none. Okay, and I'm going to talk about why. Let's just logistically write this down, and then we'll talk about why the other options that sort of seem like they might be right aren't. Okay? All will change to an existential quantifier. So you get to pick. You can pick some, at least one, or there exists. And it really doesn't matter. Sometimes it flows better with one of those versus the other in terms of the sentence that's created. And sometimes it's equally, fine either way. So let's pick one. What would you like to choose? Some, at least one, or there exists? Some. Okay. So we're going to say some next. So all becomes some. This always happens. Yes, always. I said always. You do get to say that sometimes. Sometimes it is true. Always. Now we need the opposite. All dogs go to heaven. So what would be? Some dogs what? Don't. Some dogs don't, do not, however you want to say it, but it's the opposite. Don't go to heaven.
Would it be correct to say, as an opposite, some dogs go to hell? Is that the opposite, or
well,
that's just really random?
We want to be careful, and it'll be a little bit clearer when we do the other example, because you and I, just because the way you asked that, would believe that when they die, you do one or the other, right? And I say that's probably true, and I believe that for people. I'm not really sure that I really believe that when my dog died, he went anywhere. I mean, honestly, I think he just died. So you have to really be careful about changing the language because it's not always two options about something. Does that make sense, Lauren? Okay. Let me pause right here and talk about why the word some or at least one or there exists works in this and why the word none wouldn't, or no. In this case, it would be no for the correct English. Why would this not be no dogs go to heaven? Well, the kicker is a negation is supposed to be the smallest thing you can change and make the statement false. I don't need no dogs to go to heaven to make this statement false. All I really need is one. If I have this statement and I truly believe that every single dog always goes to heaven, all I need is one example of a dog that doesn't, and my statement has been proven false. Right? If every single morning you wake up and you eat eggs for breakfast, but this morning you woke up and you ate cereal, that's all it would take for your statement, I always eat eggs for breakfast, to be false. It just takes one. Okay? So we can say some, that's fine. We could say at least one, that's fine. We could say there exists. Yes, ma'am.
Would we be able to say not all dogs go to heaven?
That's a very good question. So we're going to always change the not all ends up sounding really awkward. Because what do you mean by not all? Do you mean none or do you mean one that doesn't? So when we change it, we really are going to change it because that leaves room for question, ambiguity. Yeah. Let's try some. Okay. There are two very reasonable ways to change this statement. Because the word some could become the word all, or the word some could become the word none. What happens after that will be different, but we get to pick. And I'm going to write both of them down just so you can see them. Let's do the none version first. So we're going to change some, which is an existential quantifier, into none, which is a universal quantifier. Okay, so if I say some of my classes are hard this semester, what would I have to say next after the word none to make the statement the opposite? None of my classes are hard this semester. Don't change the hard to easy. Same thing with the heaven to hell in the last question.
None of my classes are not hard.
Okay, so some of my classes are hard. Some of them are hard. So we're going to say none of them are hard. The other one that you're talking about, Jasmine Rose, I'm going to get that one in a second. So none of my classes I need to say this semester just so that it matches. But none of my classes this semester are hard. Think about those two statements. Are those actually statements that mean something quite different? Some of them are hard, none of them are hard. Those are different statements, right? It's not like one statement is just a stronger statement than the other one. One of them says, I have hard classes, and the other one says, I don't have anything that's hard. Are you guys with me? On this one is a really good example to talk about why hard versus easy wouldn't work. Have you ever had classes that really aren't hard and they really aren't easy? There's something sort of in between. I know I have. There are classes where I could tell you, well, it's not really hard. It's just a lot of work. It's not really easy because it's a lot of work, but it's not really hard either. So that's one of those, again, it's one of those gray areas. It's not either or. You can't always classify it. You know, everything is not black and white, right? Sometimes there's a class that's not easy or hard. It's just somehow sort of in the middle. Okay? All right, so let's try what happens when we change the word some to the word all. I think that the first one that we wrote right here is the better choice because it sounds better in English. It makes more sense to our heads, okay? The next one feels just a little bit awkward to say in English. We can turn this into all, that's fine, okay? All of my classes this semester. What would I have to say? If I said all of my classes this semester are hard, is that the opposite of the statement I started with? It's not. It's just a stronger statement, isn't it? I need a statement that's the opposite. I don't have to worry about the some, all, none. I already took care of that by making sure I had the right quantifier there. That's taken care of. But what would I have to say about my classes in order to make the opposite statement? Yeah, and that's what, I think Jasmine was the one that was saying that one before. All of my classes this semester are not hard. There's nothing wrong with this statement. It's just not really quite as clear to us as the first one. It feels a little bit awkward, but it is logically correct. Okay? All right. Let's take a look at the next page. All right, what we're going to be doing with our statements now is we're going to be creating what are called truth tables. So a truth table is used to show all possible true and false patterns for statements. So we're going to first look at the negations option. So the way a truth table works is it looks kind of like a chart or a table. We're going to put our statement in the first column, and we're going to call it statement P. And you have two options when you have a statement. It can be either true or false. So I'm going to write the options underneath. So a truth table is a logical list of all the options. It's true or it's false. The next thing we're going to put in this table is we're going to put the negation of P. Okay? Negation, it should be the logical opposite. So if the statement is true, then its negation should be false. And if a statement is false, its negation should be true. So whenever we have a negation involved, we should be able to take the original statement column and just switch everything. Okay? Please be careful when you're writing T's and F's that I can tell them apart. Okay? Sometimes we get a little bit quick in our writing and they start to look a lot alike. Whether you're using capitals or lower cases, they start to look alike. So just be careful, okay? All right, compound statements are two statements that are joined with a connective. And there's lots of connectives. The three that we're going to take a look at and we're going to turn everything into are these three: and, or, and if then. Those are the three. Occasionally, sometimes you'll see, like in your book, or somebody will say, they'll use the word but as a connective. But is just another way of saying and. Think about it. I went to the supermarket, but they didn't have eggs. What does it really mean? Well, I went to the supermarket and they didn't have eggs. Okay, so when you see or hear the word but, it's really just the connective and. It's just, you know, in English we have a lot of words, right? That mean a lot of the same things. It's one of those kind of things. Okay, so we're going to look at the first one, the and statement. An and statement is called a conjunction. So we join it with the word and. It will be true if and only if both statements are true. And it is written, so we have two statements. We'll call those statements P and Q. And it's written as an upside down V. So this is read P and Q. Okay. So what we're going to do is we're going to create a truth table that looks like this. Okay. So in order to have this truth table, we need a column for P, a column for Q, and then we're going to have a column for the conjunction P and Q. So here's P, here's Q, and here's P and Q. Everybody good so far? All right, so one option is that P is true and so is Q. We're going to fill in the last column all at the same time. So right now I'm just going to write down options. So one option is that P is true, Q is true. In an organized fashion, we're going to go through our options. One option is that P is true and Q is false. Another option is that P is false and Q is true. And our final option is that they are both false. Now, in reality, it shouldn't matter what order I put these four things in, as long as they're all there. I mean, like, that's the true reality of it. But just because of convenience, and so that it's easy to check answers in the back of the book and things like that, your best bet is to put them in this order all the time. Okay? Because this is the order your book's going to do them in. It's always going to list true, true, false, false under P. It's always going to list true, false under Q. Always. Okay? So what we're going to do next is we're going to fill in the final column over here of what it means if you had two statements that were true. One that was true and one was false, and so forth. Okay? So if you have two statements that are true, and usually the example I give for these is that I teach math and I'm a mom. Okay? So if your first statement P is the person teaches math, the second statement Q is the person is a mom. Okay? Those are my two individual statements. Then I'm the line number one. I come into the classroom and I say, I teach math and I'm a mom. And you would say that statement is true because both of the individual statements are true. So the combined statement, the conjunction, is true. Okay? Dr. Auk. Many of you have had Dr. Auk. Raise your hand if you know Dr. Auk. The biggest thing you need to know about Dr. Auk right now is that he's a guy. Okay, he's a man. So if he comes in and he says to you, I teach math and I am a mom. Well, the P column was teach math, so that's true. The Q column is I'm a mom. That's false for him. If he comes in and he says that to you, the combined statement is what? It's false. It's exactly what we do in English all the time, that we would say that statement is a false statement. Okay? All right. Let's go with Dr. Gregory. Do you guys know Dr. Gregory? Okay. Dr. Gregory comes in, and Dr. Gregory says, I teach math, and I'm a mom. Dr. Gregory teaches an education, in case some of you don't know who she is. She doesn't teach math, right? I think she teaches the early childhood stuff. Is that right? Mm-hmm. Okay. So she doesn't teach mathematics, so that would be a false statement. But Dr. Gregory is a mom, so that statement would be true. But if she comes in and she says, I teach math, and I'm a mom, you would say that statement is false. I always use the same example at the end. It's Dr. Whitlock. Dr. Whitlock comes in and he says, I teach math, and I'm a mom. And we would say, no, sir, that is a false statement, right? So the only way a conjunction, an and statement, is true is if both individual statements are true. Otherwise, everything falls apart. Okay, does that look good? All right, we have to do the disjunction then. So a disjunction is an or statement, or the equivalent of an or statement. And it is true if either statement or both statements is true. And it is written like it actually looks like a V. P, it looks like a V, and then Q. And this is an or statement. So next we're going to create the truth table for a disjunction. We need a column for P, a column for Q, and a column for P or Q. Here's the cool thing about truth tables. You can always start them because the first two columns are always the same. What goes underneath P? True, true, false, false. Very good. What goes underneath Q? True, false, true, false. So that's the nice thing about truth tables. You can always start them. Even if you blanked out after that, you'd have something on the paper to get you started. Okay? And sometimes just getting started is enough to jog your memory on what happens next. All right, now we're going to do an or statement, and we're going to do the same one that I just did because it's just already fresh in our minds, right? The first one is I teach math. The second one is I am a mom. We're going to use all those same people that we just talked about. So if I come in and I say I teach math or I am a mom, that statement would be true. Both statements true means the resulting statement is true. It's awkward. We would say, why'd you say or, right? It feels strange, but it's a true statement logically. All right, Dr. Auk comes in now, and Dr. Auk says, I teach math or I am a mom. And you would say, okay, that was a weird thing to say, but that's true, right? Yeah, it's a true statement because he does teach math. Dr. Gregory comes in and she says, I teach math or I'm a mom. And you would say, again, okay, weird statement, but it's true. Dr. Whitlock comes in and says, I teach math or I'm a mom. And you would say, no, still doesn't work. No, still doesn't work. False. Okay, that's disjunctions. All right, so what we're going to do next is we're going to create a truth table for a specific arrangement of symbols. All right, so anytime you create a truth table, you will have a column for P, you will have a column for Q. Okay? So again, you can always set that up. Column for P, column for Q. And depending on what else you have over here will depend on what comes next. So if you look at the individual pieces, what have I not yet put into my truth table? The not Q, the tilde part, right? So I need a column next for not Q. Now I actually have all the individual pieces, right? So now I'm going to put the entire statement as the last piece. P, and this one's and, not Q. Okay, you guys know what to do with column P and column Q, right? So we can fill those in. True, true, false, false, true, false, true, false. Always the same. Tilde Q. We haven't done this with a full Q column yet, but we talked about what happens. If I have this column for Q that says true, false, and I'm doing the column for not Q, what am I going to have to do? Good. I'm going to switch all of them. I'm going to say false, true, false, true. All right. The next thing I'm going to do is I'm going to combine the columns that I need for my statement. I need column P and I need column not Q. So these are the only columns, the ones I've highlighted, that I'm going to consider. I don't care about column Q. It does not affect my answer. It helped me find column tilde Q, but I don't need it now. So I'm going to be looking at only these two columns that are highlighted in yellow. Do I have a conjunction or a disjunction? It's called a conjunction. It's an and statement. When is an and statement true? When both pieces are true. So my first row, I have true, false. That's a false statement because they're not both true. On the second row, I have true, true. That statement is true. Now, on the third and the fourth row, I don't even hardly have to do any work because they start out false. They're both false here, right? So I know they're not both true. I get falses automatically because I've got false in column P. And this would be the truth table representing P and not Q. Okay? Logically equivalent. Two statements are considered to be logically equivalent when they have the same truth value in every possible position. Okay? So if I took a statement that said, like this last one, I know you're writing, but just pause for a second. P and tilde Q, and I took some other statement that said something like Q or P. I don't know, some other statement. If I took both of those two statements, they're compounded and conjuncted and they're different things, whatever, and I did truth tables, and I got the exact same arrangement, T's and F's, in the final column of the truth table, that's what this is talking about, where it says they have the same truth value in every possible situation. The truth tables turn out, in the very end, identical. Those are called logically equivalent statements. The way that we write them is we write them, let's say that the truth statements themselves were P and Q, okay? We write them with 3 lines between them, kind of like a triple equality or something like that. 3 lines between them. De Morgan's law is down here. This is one of those things that I don't have written in right because my computer didn't have my symbol I wanted. There should be 3 here, so I'm going to put that in there for us. Okay. De Morgan's laws tell us 2 logically equivalent sentences, basically. So the first one has a tilde on the outside, it says P and Q. And then on the right-hand side, it says tilde P or tilde Q. These are logically equivalent statements. The second one has a tilde outside a disjunction, P or Q. This is logically equivalent to having the tilde distributed, if you will. And it's a conjunction, it's an and statement. Okay? So what we're going to do next is we're going to write the symbolic form for a couple things. Hang on. I flipped too many pages. I was like, what's going on here? I'm not on the right page. All right. We're going to use De Morgan's laws to write the logical equivalent of a statement. Okay? So again, let's just look very carefully at what we're doing when we have De Morgan's laws. What it appears to be is it appears that the tilde distributes, and when it does, it changes conjunctions into disjunctions and disjunctions into conjunctions. So and turns into or, and or turns into and. So when you're doing De Morgan's laws, you're changing three things. Okay? So let's take a look at one. We're going to use De Morgan's laws simply to rewrite notation. So if I'm writing the logical equivalent using De Morgan's laws of P and tilde Q, first P changes to what? Tilde P, not P. What is the conjunction, the and statement, change to? Or. And what does the tilde Q change to? Just Q. You change three things when you use De Morgan's laws. Three things. So what we're going to do next is I'm going to show you how you actually verify that something is logically equivalent. And I think that will put us right at the end of class. So what we're going to do is we're going to create a truth table for this statement right here and this statement right here, the one we just found as the negation. Okay? The logic, not the negation, but the logical equivalent, the negation of the tilde P and tilde Q. Okay, so the first one I'm going to create is I'm going to create a table. We're creating two tables here, right? Remember? Okay. I'm going to create a table of this one, the one I'm circling in red. So just like with a lot of algebra stuff that you've always done before, you start from the inside and you work your way outward. Okay, inside parentheses, like order of operations, PEMDAS, right? Parentheses first, inside the parentheses. So we're going to have a column for P. We're going to have a column for Q. That always happens. What else is inside the parentheses? Not Q, right? Tilde Q. And then inside the parentheses is everything, right? So we've got the P and tilde Q. And then our final statement is that we're going to negate that. So we have the tilde of, or the negation of, P and tilde Q. Okay. What goes in the P column? True, true, false, false. What goes in the Q column? True, false, true, false. What goes in tilde Q? We already did this too, right? False, true, false, true. I'll remind you how we do this. We look at the correct columns that correspond to this. We need P and tilde Q. When are two, I said that twice and I still don't know what I meant. When is a conjunction, an and statement, true? When they're both true. So in the first row I have true, false. That would be false. The second row I have true, true. That would be true. Third and fourth row are both false in the P column, so they are both false. Okay, so that is actually what we already did. We did all of that prior to this particular problem. The next step is different. It has the tilde on the outside of the last column. So I really need to only be looking now at this last column right here to make my decision for this column that I'm on right here. I just do the opposite. So what will it look like? Nice. True, false, true, true. Negations are nice. Okay, I wanted to see if I had more space. I don't. That's okay. So we're going to write the other table over here. We're going to have the second table, which is looking like the one in blue that I'm circling. Okay? So using the one in blue, again, I always start out with a P column and a Q column. None of that's ever going to change. P, Q. Now I look at my statement itself. What else do I need for my statement itself? Encircled in blue. Not P. Yep. That's all I need, individual statements, right? And then I need the combination of all of it, which was what? Not P or Q. Is everybody with me? I'm looking back at this part right here. I'm trying to verify that what I did in part, or in question 3, actually is logically equivalent to the one that I'm actually being given the problem for. P and Q stay the same. What's P going to be? True, true, false, false. Very good. And Q? True, false, true, false. All right, tilde P, not P. What will not P look like? So I need to go back to column P. So I have false, false, true, true. Now I'm looking at these two columns, the tilde P column and the Q column. When is an or statement true? If either one is true, or both, right? So my first row says true, false. What is that? That's true. My second row says false, false. What is that? False. Very good. My third row says true, true. That is true. And my fourth row says false, true. And that's also true. Or statements, either one or both are true. And so what we're actually doing is we're verifying that when I look at the last column of each table, what do I see? The exact same true-false arrangement. And that will always happen if you have logically equivalent statements. And we'll stop there for today.